Hello and welcome to our fourth lecture. It's now 5 past noon, so we should start. In the first 3 lectures, we have talked about first the relativistic particle and then the relativistic string, including a brief outline on how we will go about to formulate the quantum theory. In the part 3, which we have begun during the last minutes of the third lecture, we will now deepen our understanding of the worldsheet perspective of string theory and learn about conformal field theory. Before I start, are there any immediate questions? Questions from maybe left over from the last lecture? Okay, this doesn't seem to. There's one remark in the chat. Somebody asked about conditions in equations 23 and 24 in part 2. I'm happy to revisit this. We have good time. So let's go back to part number 2 and find these equations. Oh, it must be a bit before this. 23, 24. Yes. Okay, so what you have to do here is, if we go one line, couple of slides back, where we introduce a worldsheet mentor. So you see pi mu is p0 mu, so this equation, and you have to take this equation and then multiply it by whatever is requested. So in one identity we compute the square of this object, in the other constraint we multiply it, I think, with x prime mu. So you bear in mind this expression, and now we go forward again to 23, 24, and you have to take this equation in one relation, you multiply it with x prime mu, and this gives 0. Now pi mu looked a bit complicated, but it's a fraction, so it can only become 0 if the numerator becomes 0. And then in the second equation, you need the square of the slightly complicated expression pi and compare it with the square of the vector x prime. And again, because pi is a complicated looking fraction, some simplification must be happening if you square it, which allows you to combine these two terms to be 0. Just a second, I need to drink something. Yeah, but it only takes a few lines to see this. Okay, good. I hope this is okay. Okay, good. So that seems to be a good. This seems to have given an idea how to go about this. So let's go back to where we left off and just go quickly again over the sheets that we have, over the, what's the word again, the slides that we have already looked at last time. So our idea is to get an idea about conformal field theory will be experimental. We will find out and detect certain properties. Our starting point is the Polyakov action in the conformal gauge, and then we truncate it down to one single string coordinate. And equivalently, we can say we have a 2-dimensional field theory of just one free master scalar. And we can write it down in various coordinates. We have our coordinates sigma 0 and sigma 1, where one is time-like, the other space-like. But sometimes it's useful to use the light cone coordinates. So I give you in Formula 1 both for reference. And then here I gave you as a reference the equations of motion. We don't consider interactions, which would correspond to the worldsheet splitting or different worldsheets joining with each other. So if we take a closed string, then the worldsheet is a cylinder. And on this cylinder, we do two things. We make a Wick rotation where we make the worldsheet time imaginary. That's what we do here. And this then introduces a coordinate W. Then we have a Euclidean cylinder. And then we perform a conformal map to the complex plane. And okay, different conventions we define in books. In my conventions, it looks like in Formula 5. And then, yeah, I showed you a picture last time. Maybe I don't need to show it again, but you can then work out a translation, how things relate from the old language of the Lorentz signature cylinder to the Euclidean plane. Most importantly, time translations are now dilatations or scale transformations. Therefore, time ordering is radial ordering. And translations along the string become rotations in the complex plane. There's a very natural relation between light cone coordinates in Minkowski's signature and what is called partial holomorphic or Wirtinger derivatives in the complex plane. These partial holomorphic derivatives are complex linear combinations of real derivatives, and here, as usual, x and y are the real and imaginary part of a complex number. In particular, if you apply this to tensor components, then light cone components become holomorphic or anti-holomorphic components, which we label by indices z and z bar. These are the labels that worldsheet tensors have if we work in the complex plane. And here is then, for reference, again, how the scalar field on the complex plane looks like. Equation of motion is now the harmonic equation, which can be solved by one independent function of z and an independent function of z bar. Being only a function of z is understood, or this notation is meant to understood that the function is in holomorphic. And with regard to the second function, we have two possible interpretations. Most natural one, if it just makes a continuation, then x bar will just be the complex conjugate of x of z. But since everything decouples between left and right moving sectors, which now becomes barred and unbarred sectors, then also has the option to treat x and x bar as two independent complex variables. That kind of doubles the dimension, so that we are now in a complex target space, but that sometimes gives one the opportunity to go back and forth between Euclidean and Minkowski's signature. Good. Important object energy momentum tensor. This I've now also written out here in the new variables. And as for the light cone coordinates, the tracelessness is a vanishing of the mixed component. And the conservation equation now becomes the condition that the ZZ component is holomorphic, that is only a function of Z. And the Z bar component is only a function of Z bar. Now, let's talk a bit more about conformal transformations in 2 dimensions. So we said reparametrization, or also called diffeomorphism, is called conformal if it changes the metric only by a so-called conformal factor. And this is a function which is positive everywhere. In Formula 10, I've written this as a finite transformation, and then if you expand it out, then the infinitesimal form is given also here. If we work out explicitly the change of a metric under an infinitesimal reparametrization, then the result is Formula 11. So here, when I say infinitesimal, I didn't write explicitly a small parameter epsilon, but it's then understood that this function here, psi alpha, the so-called generating vector field of the reparametrization, is infinitesimal, so that whenever we expand out, we can neglect any terms which are order epsilon squared. The variation is defined in this way. We take the transformed and the original tensor at the same point and compare. And if you work the transformation for the metric out explicitly, then you will get this formula here. And this is all expressed in terms of partial derivatives. And that's a useful formula. However, one would often like to see that this expression is actually a covariant expression, because after all, the worldsheet metric is a tensor. So its variation should also be a tensor. And this can be done by realizing that this expression can be written also in terms of covariant derivatives. So if you're familiar with covariant derivatives, you can check this. And as a second remark, there's another kind of derivative that one can define, which relates tensors to tensors, in the so-called Lie derivative. And what we have written down here, namely comparing a transformed tensor and the original tensor at the same point, is actually up to a sign the very definition of the so-called Lie derivative. The Lie derivative is a derivative that measures how a tensor changes under an infinitesimal transformation generated by a vector field psi. There's a minus sign here. Sometimes in the literature you will find a plus sign. This question of the plus or the minus sign is related to whether we take our transformation to be a so-called passive transformation, meaning we make a coordinate transformation, or a so-called active transformation. Active transformation means that we really take a point on our space, in our case a worldsheet, and move it to a different point and express how this happens in terms of coordinates. Good. Leave it to you to verify that change of metric under an infinitesimal reparametrization takes the form 11. And if you are familiar with covariant derivatives, then you can repackage it. And if you want to read up a little bit on the Lie derivatives, then you should also find that this is the correct definition for a Lie derivative, and that for a second rank tensor, formula 11 gives you the expression in terms of partial derivatives. Now, what are the infinitesimal transformations which preserve the conformal gauge? In Minkowski's signature, is this statement. In Euclidean's signature, is this statement. So the statement is the variation of the metric that we have fixed is proportional to the metric itself with an arbitrary function. If you work this out, then you find in Minkowski's signature this relation here on the components of the generating vector field. And this then means that the new sigma plus, which I call sigma tilde plus, is only a function of sigma plus and not of sigma minus. And the same applies to sigma minus. Sigma tilde minus is only a function of sigma minus. If you write in general coordinates, then this becomes the wave equation, where the wave operator is taken with respect to the old variables. But in the Lightcon coordinate, one sees very nicely that the special about conformal transformation in Minkowski's signature is that it does not mix the two Lightcon directions. In Euclidean signature, it is similar. What you get is that the vector field with the upper index z is not dependent on the variable z bar. So in other words, the component psi z, upper z of the vector field is a holomorphic function. Or in other words, our coordinate transformations are holomorphic. The new coordinate, which are called here w, is a holomorphic function of z, and w bar is a holomorphic function of z bar, where we have the choice to either say w bar is a complex conjugate of w, but one can also extend the theory a bit by treating the two variables as being independent. Good. Now, here is a bit more about conformal transformations on the cylinder and how we can parametrize them. Ah, yeah. Okay. Before there's one thing that I forgot. What this here shows is something important here, if we are in Euclidean signature, then we can note that we have worked out that we wanted to have a transformation which is conformal, and we found the conformal transformation is the same thing as the holomorphic transformation. So that is something that you might have heard about if you have done a course on functions in the complex variables. In the complex plane, conformal transformations, that is transformations which preserve shapes, or if you like angles, are in one-to-one correspondence with holomorphic transformations. It's precisely the holomorphic functions which generate for you conformal transformations. And that is, of course, very useful because we can now be able to use methods from the theory of complex functions in our pursuit of conformal field theory. Good, but now I'm back on the cylinder in Minkowski's signature and would like to somehow parametrize the conformal transformations. Here I write down the general conformal transformations. The function f plus is an arbitrary function of sigma plus, arbitrary except that it must be periodic, because sigma 1 is periodic for the closed string, and therefore sigma plus is also periodic. Now, but periodic functions, I know that there's a kind of basis in which I can expand these functions, and this is nothing else than the Fourier series, and then I have here infinitely many coefficients fm, the Fourier coefficients, and these parametrize all possible periodic functions that I can use to generate an infinitesimal coordinate transformations. Now, one way of thinking about these transformations is in the form of generating vector fields, and the generating vector field is this vector field Lm, which I write here. And if I take the commutator of these generators, I get an algebra, which is called the Witt algebra. But before continuing, let me stress or expand a little bit on the following form. What I'm using in this formula here is that one can regard vector fields as differential operators. And let me add a few side remarks on this. So this example here is in a generic situation with some coordinate x mu, and we have a vector field, and we write this vector field expanded out in the basis, where the basis vectors are just the partial derivatives with respect to the coordinates, with respect to the coordinates that we have, and then we have components which are functions of the coordinates. And this interpretation of vector fields as differential operators is useful. For example, I now have a correspondence between vector fields and infinitesimal transformations. So let's assume f of x is a function. Then the vector field psi applied to this function f generates the infinitesimal transformation of this vector field in the following form. The application of a vector field to a function is just as a differential operator, and then you see what this does. It computes the directional derivative of the function in the direction of the vector field at each point. But this is precisely the linear term in the Taylor expansion that I get if I shift the argument of the function by the amount given by the vector field. And this shows you explicitly how vector fields generate infinitesimal transformations on functions, and by extension also on tensors. Our example here was the infinitesimal transformation where sigma plus is changed by an arbitrary periodic function. The basic operators that generate these are these differential operators, and the function to which I apply this is just, in this case, sigma plus the coordinate, which is also a function. Then you see here, if I write an infinitesimal transformation, and here I've written an explicit epsilon to make clear that this is an infinitesimal transformation, then because d sigma plus by d sigma plus just gives me 1, I see here that this shifts sigma plus by one of my basic periodic functions. So I can describe all possible conformal transformations in the sigma plus variable in this way by this set of generating vector fields. the realization as of vector fields as commutators also explains how I can define the commutator of vector fields. This is called the Lie bracket. So the commutator of two vector fields is just the commutator of the corresponding differential operator, same way as we would do it in quantum mechanics. When working out such commutators, always useful to imagine here that this is then ultimately applied to a function, and then using that, if you just have two derivatives on some functions and d mu and d nu commute, the part which not commutes is isolated here, and this is then the new component of the commutator. And there's this formula you can then also, yeah, okay, this is the next thing is what I don't want to show. So let me go back to my slides here in part 3 and probably around here. Yeah, this is then the algebra that you want to show. This is then the Lie algebra of infinitesimal conformal transformations, which is called the Witt algebra. It's since we have infinitely many infinitesimal conformal transformations, it's an infinite dimensional Lie algebra. It has a particular structure, and you can see here that the commutators are consistent with the integer labels which I give here. So we have a object with an index m, commutate with n, and what I get out has the index m plus n. That is called a Z-graded Lie algebra. Z-graded means the commutator is consistent with these integer labels that we put on the generators. Good. It's a short exercise to verify that this commutator holds. And of course, we have talked about sigma plus, but for sigma minus, I have a similar set of relations. So I have two copies of this Witt algebra. And this is my Lie algebra of infinitesimal conformal transformations on the Minkowski cylinder. What is now, for the interpretation, useful to note is that L0 and L0 tilde are up to numerical factors d plus and d minus, and L0 plus L0 tilde is therefore d0, the derivative with respect to sigma 0, and therefore the generator of sigma 0 of worldsheet time translations, and therefore it really makes sense to call this the worldsheet Hamiltonian, because L0 plus L0 tilde generates translations in worldsheet time, and in the same way, the difference is proportional to d1 and deserves to be called worldsheet momentum because it is a generator of sigma 1 translations. The subalgebras generated by L0, L plus, and L minus play a special role, as we will see in a moment. And if you compute these commutation relations, then you find that they are the commutation relations of the Lie algebra SL2R, or equivalently SO2, 1. So this looks like SO3 or SU2, which you know from angular momentum, except that there is a relative minus sign in the commutation relations somewhere. You can verify that this is the algebra satisfied, and we have two copies of this. Now, why is this interesting? Well, there's a general statement about what is the algebra of infinitesimal conformal transformations. And in Minkowski's signature in general, it is SOD, 2. And I've compared it here to the Lorentz Lie algebra in d dimensions. This is SOD minus 1, 1. Maybe it's a bit more explicit to do it in 4 dimensions. In 4 dimensions, the Lorentz algebra is SO3, 1. And you get the corresponding conformal Lie algebra by adding plus 1 in every slot. So SO4, 2 is the Lie algebra of conformal transformations in 4 dimensions with Minkowski's signature. Therefore, what one expects in d equals 2, we would expect that it is SO2, 2, which turns out to be to decompose into 2 copies of SO2, 1, or if you like, SL2R. And this is precisely what these L minus 1, L0, L01 and their tilted partners R. But as we have seen, in 2 dimensions, we are in for a surprise because we have infinitely many further generators, L2, L-2, and so on. And this is what makes conformal symmetry extremely powerful when we are in 2 dimensions. So that was a cylinder. Let's briefly review how this looks in the plane. So I said in the plane, my condition is that the z component of the vector field is independent of z bar. Therefore, conformal transformations, which I've now written in infinitesimal form, are generated by holomorphic functions. I already mentioned holomorphicity can be written in terms of the partial holomorphic derivatives as dz bar f equals to 0. This is equivalent to the so-called Cauchy-Riemann equations, which you have seen if you have encountered holomorphic functions before. And one can say equivalently that the real and imaginary part of a holomorphic function satisfy the harmonic equation. More interestingly, the generators now take this form. That's similar to before, except that we now have a complex variable, and therefore the resulting Lie algebra, which we get, has the same structure, but we can now regard our generators as complex. And normally we would then regard the operators LM bar as a complex conjugates, but as I already mentioned earlier, you could also treat them as independent complex variables if you like. That's sometimes done in the literature, therefore I mentioned. In practice, we just look at one sector at a time, so we are not particularly sensitive to this difference. Now, in this formula here, we are allowing arbitrary integer powers. So as long as we are on a cylinder, or part of a cylinder, which is a complex plane with the origin removed, then this does not cause any problem. But of course, if we go to the origin, z equals to 0, which represents the infinite past in terms of string evolution, then those operators where we have negative powers will have a singular coefficient, and therefore the vector field is not defined as z equals to 0. And similarly, you can also define holomorphicity at infinity. This is then most clearly seen by making a coordinate transformation. So you would, sorry, let me write it here. You would then work with the coordinate w equals 1 over z, which becomes 0 if z goes to infinity. And if you rewrite vector fields, or more generally tensors, in terms of this coordinate w, you can talk about the point at infinity in the complex plane, and then you will again find by looking at the variable w that part of your vector fields are singular if you are at z equals to infinity in the infinite future. So not all infinitesimal conformal transformations become really finite conformal transformations on the Riemann sphere. What one can show, and that might be among the next set of exercises, which I'm probably rolling out next week or so, what one anyway can show is that is precisely the subalgebra SL2C and only the 3 vector fields L-1, L0, and L1, which are regular on the whole complex plane extended by the point at infinity. So there's only 3 vector fields which generate transformations that are well-defined transformations on the Riemann sphere. And if you write the corresponding group action, so these are now finite transformation, then on the extended complex plane, meaning complex plane allowing the value z equals to 0, these act as fractional linear transformations where the coefficients A, B, C, D form an SL2C matrix. And of course, SL2C matrices are unimodular. So there's one relation between the 4 entries. So there's only 3 independent entries corresponding to our 3 generators. Okay, and here's the exercise. Verify that these are the only vector fields, or exactly those vector fields which are regular both at 0 and at infinity. So our conformal transformations somehow divide up into a general infinite set of conformal transformations which are well-defined infinitesimal transformations. And then we have a special set of three which define in everywhere well-defined finite group action corresponding to the group SL2C. Good. Now, one of the things that we want to do with the conformal field theory formalism is to formulate the quantum theory of strings. And to motivate this, I will first apply the, so to speak, conventional quantization approach to the free scalar field. And then we will make some observations, and then we will turn the logic around and get a new way of setting up the quantum theory and have a different language, which is very useful. So how do we normally proceed when we quantize a quantum field? Well, we solve the classical equations of motion and then get a mode expansion, which for us, from the previous results and continue to the complex plane, takes this form here. So we have, as a constant term, the term proportional to p has become a term which is logarithmic in z. And then we have an infinite series of positive and negative powers of z and z bar with coefficients alpha n tilde. So this is, if we ignore up to the logarithmic term, this is a Laurent series, or to be more precise, a formal Laurent series, because we admit arbitrarily negative powers here. Good. So that is input, and then one imposes canonical commutation relations. This is something that we already discussed. So we now have only one coordinate or one field, one scalar field. So we don't have additional indices, and it's an XP commutator and alpha m. And we only talk about the holomorphic sector. Now the anti-holomorphic sector is just a copy of this. How then do we proceed? Well, we want to represent these commutation relations, and to do this, we define a ground state, which is annihilated by half of our operators. For the zero mode or XP algebra, we say the ground state should be a translation invariant. We are using here that P is, in string theory interpretation, the translation operator. So we take our ground state independent to be annihilated under this operator. And then we pick the alpha m's with the positive index m as the annihilation operators for this ground state. And then our Fock space, which represents the commutation relations, will consist of P eigenstates or momentum eigenstates. And then we have creation operators alpha m, which in the string theory interpretation switch on all these oscillations. So let's compute something. Simplest thing is a two-point function where we have a vacuum correlator of two operators. And for reasons that will become clear a bit later, I don't take the correlator of x with itself, but I take the derivative of x with itself. Now, so I take these objects as operators and sandwich them between ground states. And here's a simplified notation. I will admit the argument if by the derivative is clear on at which point this is evaluated. And what I claim is that up to numerical factor, this gives us a second order pole in z minus w. So how would we compute this? Let me show. So we have a mode expansion for x, so we have a mode expansion for the derivative. And if I define alpha 0 to be suitably related to p, I can write this as a single sum over n, essentially a formal Laurent series alpha n set to the minus n minus 1. I can substitute this in, okay, and then I get a twice infinite sum over m and n with the operators alpha m stuck between ground states, and then everything dressed up with some powers of z and w. Now comes the standard trick how one evaluates commutators or correlation functions in a free quantum field theory. One uses that certain operators are annihilation operators, either acting on the in or ket vacuum or on the out or bra vacuum. And for that reason, I can truncate my sum. The m sum is only over positive numbers and the n sum only over negative numbers. But if I have this form, then again using that half of the operators are annihilation operators, I can replace the product by the commutator. Now, the commutator of alpha m with alpha n is not an operator anymore, but just a number. And in this way, I can evaluate this, and then the correlation function is, or this quantum states are gone away. I just have function left, which is given here. And if you stare a little bit at the function that we find, then what you see is that this is the derivative of the geometric series, and therefore it adds up to 1 over z minus w squared up to a numerical factor. Now, since this infinite series is related by differentiation to the geometric series, it has the same radius of convergence. So this sum only converges if modulus of z is larger than modulus of w. I don't know whether you can read this, so I add this. This is for convergence. Sorry. Okay, it's not so nice, but well, you see this condition here, and it also, if you look at this, the slides, you will find it. Okay, so the sum only converges if the arguments here are radially ordered. Z must be further out than W. So this is our result. But now we observe that the function that we find is in fact defined by analytic continuation for any non-coinciding arguments. Despite that the operator product that we evaluate only made sense, or that the sum only converged if we had radial ordering of the argument, by analytic continuation, we can define the correlation function for all arguments which are non-coinciding. And this illustrates some general facts about Euclidean correlation functions. So first is, of course, that is something that we understood already. Time ordering is radial ordering. But what we have seen explicitly in this example is that Euclidean operator products are only defined when radially ordered. This is understood in the future. Sometimes one writes an extra symbol R for radial ordering in front. But since only radially ordered product makes sense, I will, when I write down operator product, then it is understood that it is radially ordered. Another thing that we have seen in our exercise that it is crucial for getting functions that we evaluate expressions on the vacuum. So the slogan is that operator products converge on the vacuum. Yeah, if we evaluate these operators themselves are formal infinite series of positive and negative powers of z multiplied with some operators. So that's kind of formal object where I cannot really talk about convergence. But when I evaluate the products of such operators between states, then I can evaluate them, and then they become functions or infinite series, which then may or may not converge. And finally, we get radially, or out of our radially ordered product, we get correlation functions, which we can continue analytically. And we see here z minus w squared is symmetric under exchange of z and w, and this is generic for correlation functions of bosonic operators in the Euclidean. They are always symmetric. We won't have the time to talk about fermionic operators, but there the correlation functions would be totally antisymmetric. So if we would talk about a Dirac field, this two-point function would be something like 1 over z minus w. And this is, of course, antisymmetric under exchanging z and w. Good. But now comes the big idea. We turn the whole logic around and we treat operator products, or is it called operator product expansions, because you take a product of operators and then expand it in terms of other operators, and this might be a finite or infinite sums, therefore it's called an operator product expansion. We take these to be fundamental and then either work exclusively with these OPEs, or if need be, we can reconvert them into commutators. That's what I want to explain now in this example by doing the example backwards. So what we will now do, we will derive the alpha-alpha commutator by starting with the OPE for the operator product of derivative of x with itself. Now, the form that we postulate is formula 34, where we say the following: this will have a singular and a regular part, and the singular part which we postulate is the result that we found previously, which we now turn into a postulate. And then the operator product might have further terms, but these terms are regular for z goes to w, and therefore this so-called normal ordered product does not contribute to the vacuum expectation value. So the singular part of the OPE is the part which gives us the vacuum correlation function for these operators. Now, if you have encountered quantum field theory before, you might have heard about other ways to define normal ordering. Here, normal ordering is defined by taking just the regular part or splitting off the singular part of an operator product expansion. Since we know to express x and dx in terms of alphas, we could also have applied the standard rule for normal ordering from quantum field theory, which is put all annihilation operators to the right of all creation operators. And I've written down here what this means for alpha m, alpha n. Colon means normal ordered product. And then if I have one positive and one negative index, then I have to be careful and put the annihilation operator to the right and the creation operator to the left. If both are creation or both are annihilation operators, then this doesn't play a role. And of course, if the two operators commute with each other, it also doesn't play a role, but does play a role when the two do not commute. Now, I leave it to you to verify that in this particular example, these definitions of normal ordering are equivalent to another. A priori, they don't need to, and in general, they won't, because such ordering prescriptions can always be ambiguous by finite terms. Yeah, so the prescriptions could have differed by some kind of finite term. But in this case, everything matches exactly. But now back to the main business, so that we can conclude this within this lecture. We want to take the OPE 34 and derive the alpha-alpha commutator from it. So how would we go about? Now, first of all, we can, if we have a given delta x, extract the alphas out of it by the residue theorem. So this is the formula that alpha m. It can be projected out by taking the functions that we are considering, dx, dzx, multiplying by the appropriate power of z, and then performing a contour integral in the complex plane around the origin. So let me remind you briefly of the residue theorem. This is reviewed here. So in the theory of complex functions, this is formulated for Laurent series like here. Now we are a bit more generous. We also allow arbitrarily negative powers. But if you expand it out, there will be coefficients for all possible terms, like 1 over z squared and 1 over z, and constant term and z, and so on. But the residue theorem tells you if you perform this contour integral, then you always pick out the so-called residue, which is the coefficient of the 1 over z term. Now, if I want, say, extract a to the minus 2, then I would put the same function in the commutator, but multiply it by z, so that I cancel one of the powers of the z squared and extract a minus 2 instead of a minus 1. So in this case, in this way, one can extract out of Laurent series the coefficients using the residue theorem. It's always understood, by the way, that the contour only includes the singularities or poles at z equals to 0. Of course, a function might have more poles, but we indicate here for clarity which of the singularities we want to include in our contour integral. So now we can go back to our slides. Where are we? think we are about here. Yeah, we are about here. So this explains how I extract this. And then in principle, all I need to do is to compute the commutator. And for convenience, I've put the numerical factor here to make the computation a bit less cluttered on the right-hand side. So I have this commutator. But now we have our problem that we take, commutator means we take here the product in two different orders, but Euclidean operator products are only defined when they are radially ordered. And in order to interpret this commutator, I therefore need to rewrite it or reinterpret it. And the way it's interpreted is as a choice of integration contour. And again, for this, I should show you a drawing, which I think is still in this here. So if we evaluate our commutator, we have once an ordering where Z modulus is larger than W modulus, and in the second term, it's the other way around. Now, if you think in terms of integration contours, if modulus of Z is larger than modulus of W, then the integration contour around Z equals to 0 will also have to include any singularities at Z equals to W. Whereas if the ordering is in the other way around, then the contour integral over Z will only encircle the origin. Therefore, if I take the difference between these two expressions, I will end up with a contour integral which only includes the point where the arguments Z and W coincide, and the Z equals to 0 contribution cancels out. And this is what I have written on my slide. If you now go back to my slide, this is what I've written here. We take here a contour around Z equals to W, and this here is the radial ordered product dZx dWx. And now we can insert our operator product expansion here and evaluate the contour integrals. I think we have time to do this. So if we do this, if you insert the OPE, what then remains is here we have this second order pole from the OPE, the factor minus 1 to the 4, which I have written to the other side, has cancelled. And we have to take now the Z integral first around Z equals to W. And according to the residue theorem, we will pick out the first order pole. Now, if you look first at this integrand here, we don't see a first order pole, but there is one there which is hidden. And to see this, we use the binomial formula to write out Z to the M in terms of W and Z minus W. And if we expand it out with the binomial formula, then we'll start with W to the M. And then comes the term M times W to the M minus 1 times Z minus W. And this Z minus W, this particular term, this is the only term which will contribute. We see this here, because in this particular term, we have a cancellation where we reduce the denominator to Z minus W and get a contribution. And this gives us then this result. Then we have one further contour integration to perform around W equals to 0, but this just picks out the term where the coefficient or the power of W here is minus 1, and this gives us exactly the right answer for our commutator. So that is the contour integration method for getting commutators out of operator product expansions, and that is something that we will use frequently and which is one of the most important techniques we learn in this course. Good. I think we are almost done, but let me just give you a sneak preview of what we are going to do next. We want to also talk about the energy momentum tensor, and the energy momentum tensor is a product of the derivative of x with itself. Classically, that makes sense, but we have seen that quantum mechanically, this product has a second order pole, and the coefficients coincide, and therefore in the quantum theory, the energy momentum tensor is defined as the normal ordered expression. And okay, I'm reminded that I should now wrap up, which I will do. So just to conclude the sentence, we have seen that if we have an operator product expansion, we always have a singular part and a regular part. So the normal order product is the regular part. And for the singular part, I now introduce this notation here, which is the so-called contraction. And this will next time lead us to applications of the Wick theorem, which we will then use in order to perform operator product expansions, which involve the energy momentum tensor. Okay, my time is up, so I think I should stop here. Are there any immediate questions that I should answer? Okay, let me check whether there's anything in the chat. No. Okay, good. Then we are, I think, finished for today. If you have questions, you can let me know through the course forum or by email. And yeah, otherwise you have the first problem set, which I posted last time. So I suggest that you try to get on with this so that I can make solutions available next time. And probably next time, it might already be time to release then the next set of questions. Okay, this and all. I'll stay until everybody is gone. So thank you for attending. And in those times, I would like to add negative, yeah, in the right COVID sense. Please stay negative, be safe, have a good week, and looking forward to seeing you again next week. Bye bye now.